iC-House Integrated Circuits.
Hello and a very warm welcome from my end. So my name is Silvan Ettle. It is a pleasure to introduce you to our new high resolution and optical encoder device, the iC-RT2624 today. So the roadmap is going to be, we will talk about encoder principles, some encoder performance specs before diving into the latest feature set, highlighting a few features that are integrated in the chip. Then we'll show the evaluation kit, what is available for you if you want to get started. And last, I'll do a live demonstration setting up a 26-bit optical absolute encoder here within minutes. As Henrik said, please, you're more than welcome to ask questions. We'll do our best to answer all of them at the end. Rest assured, all questions will be answered. And yeah, thank you for participating. Without further ado, let's dive into the application and what you can build with this new device. So the encoder principle of the iC-RT2624, well, obviously it's an optical device, so it does contain a sensor window with some photosensitive areas. It comes in a 7x5mm QFN package, operational conditions 3 to 5.5 volts, minus 40 to 125 degrees C. And as it is optical transmissive, there is an LED required on the other side of the sensor, which illuminates a code disk. Collimated light is very much recommended here. Spot size, a good starting point is 3.4mm for the illumination, but there are some degrees of freedom you can use for sure. And yeah, in terms of wavelength or LED color, 400 to 900 nanometer is the spectral sensitivity of the sensor front end. Well, last but not least, one main characteristic, it's an absolute encoder device. What does that mean? Well, after power on, the absolute angle information is right there. No motion required whatsoever. Therefore, the system uses a pseudo-random code here on the inner track of the code disk. Yeah, this is related to the inner track here. That provides a coarse absolute position. Within that coarse absolute position, the incremental track is used to generate sine cosine that is interpolated on chip with 16 bits per sine cosine cycle, ending up in the 26 bits of resolution. Speaking of which, encoder performance, well, what can you expect from the device performance here? It delivers 26 bits of angle resolution with a 26mm outer diameter code disk. Resolution is one side of the medal, accuracy the other. To increase the accuracy, we have an on-chip eccentricity compensation that gets rid of, well, what most of you might be familiar with. If you have a radial runout of a code disk that is not perfectly centered on the rotating shaft, you get this long wave angle error over 360 degrees, and the eccentricity compensation just gets rid of most of this error. No need to look at the small numbers here because I'm showing them here. Typical angle accuracy that you can achieve with this device is below 0.01 degree. That said, this number here is a little bit on the conservative side, because if we talk about arc seconds, so this would correspond to 36 arc seconds. If we're talking arc seconds, of course, the quality of the overall system design, mechanics, code disk, and so on is extremely important too. Well, I've seen single-digit arc seconds of absolute accuracy with this device. It's possible. In terms of repeatability, 10 times better, roughly, than the absolute accuracy. So you can reach 0.001 degree of repeatability, corresponding to 2 to 3 arc seconds in that range. And well, Resolution accuracy is one thing. You'd like to have the position data as fast as possible to have a smooth control performance. And therefore, this device is super fast from a change in the optical front end to an output of the position data at the pins on the output side. Below 1 microsecond of sensor latency, I think this is a top-notch number here. RPM, well, how fast can you spin the code disk to use the sensor? Of course, it depends on which code disk is used, but for the standard code disk, 26 millimeter here, you can go up to 30,000 RPM. Well, what key applications does this sensor fit? Well, obviously, high-resolution encoders, housed encoders with bearings, probably an IP sealing, something like this. There is a perfect match, of course. But also modular kit-style encoders directly assembled in the field to like a motor or something. There we need some other features as well, which I will present on the next couple of slides. And in terms of system design, well, motor feedback systems, classic servo motor feedback would be one of the key applications, but also angle measuring systems if you want to go really high-end, making use of the arc seconds of accuracy that you can achieve with the device. All right. Performance usually comes with some price, the price of a tight assembly. For this sensor, it does not. Okay, that must be clear. This is one of the main excitement features of the sensor. The production and assembly is super relaxed. So in tangential direction, sensor versus code disk, the static displacement tolerances are plus minus 0.5 millimeter. In radial direction, same number, plus minus 0.5 millimeter of static displacement tolerances. The sensor can take some rotation in the XY plane up to plus minus 2 degrees. And speaking of the modular kit-style encoder motor feedback applications, you want to have a certain degree of freedom in the Z-axis as well. So to compensate for some axial play, for example. And this is also a very good number here. So this high-resolution device can go up to 0.8 millimeter of air gap between the sensor package surface here, shown here, and the code disk surface. Of course, you can go as close as possible. Yeah. Okay, that's it for assembly tolerances. What about operation, robustness in operation, high availability? We all are aware of reducing downtimes in machine parks. What about availability? We integrated a contamination-tolerant sensing technology here. So here you can see that the top side of the chip in this middle rectangle here. This is the sensor window with the two sensing elements here, and well, it consists of. Here you can see the code disk moving above the sensor window. It consists of the upper high precision phased array that is there for the high resolution and to provide the high accuracy. So this is the analog front end, so to speak, and the bottom area here is the pseudo-random code scanner that provides this coarse absolute position, and it incorporates a real-time bit error correction. So up to 5 bits within the field of view of the sensor can be corrected in real time if you do have a bit flip. Imagine you do have a sudden contamination. If you do have a small defect of the code disk that would flip one to a 0 or vice versa, this chip can compensate it in real time. A picture is better than 1,000 words, right? So I'm happy to show you something right out of our R&D department. So this is kind of a recap. This was like a major milestone, glimpse into early development I've written here. Those were the first real-world contamination tests we did with the first prototypes for this new scanner design. And believe it or not, this encoder system you see here still provided a plausible absolute position. All right, so we have high resolution, high accuracy, easy installation, easy assembly, proper robustness for operation. What about design flexibility? So the system, or the iC-RT2624, got its name from the standard code disk it uses. So it is a 26 millimeter outer diameter code disk with 1024 CPR of base resolution, so number of lines of the incremental track. If you do have a certain installation space that needs to be fit, that 26 millimeter might not work out, right? No worries at all. The sensor features FlexCode. So from 20 millimeter outer diameter to like almost any diameter that is required for the application, there can be a code disk design according to the needs of your installation space. So if you, for example, require a 39 or a 50 millimeter code disk, please reach out to us with your desired requirements, and we can talk like outer diameter, inner diameter, and some idea where the chip should sit on the PCB. Of course, when you scale the code disk of such a system, it's a fixed pitch system, so the line width is not changing. There might be some odd CPR line count on the code disk. Yeah, that is not like the classic binary resolution that you would expect from a code disk. That does not matter at all. So all the encoder interfaces are freely programmable. You can just program the desired output resolution that is required for your application. Of course, well, the obvious ones for the absolute angle or the absolute position, BIS, SSI, or SPI, which are available in parallel, by the way. It's not a choice. You could use both and simultaneously. Also for the quadrature output, A, B, Z, you can just program the number of pulses that you would like to have on 360 degrees full rotation. And then there are two sine cosine interface ports, differential interface ports. One is, let's say, the classic analog sine cosine that is related to the native CPR, the native resolution of the code disk. That is, by the way, routed in a safety-ready fashion throughout the chip, meaning that it avoids cross dependencies in this signal path. So if you do have a SEER requirement that we could make use of this sine cosine signal path, feel free to reach out. We can discuss potential approaches here. And aside from the classic analog sine cosine related to the native resolution of the code disk, we have a sine cosine generator, and this really is an excitement feature. You can just program whichever sine cosine resolution you would like to have independent of the native resolution of the code disk. I make an example. Think of a product line you want to build, a 36, a 54 millimeter encoders, so two products, and you would like to have the classic 1024 or 2048 sine cosine output for both of those devices. You just need one sensor, two code disks, and you can just program it. Plain simple. Another cool thing about this sine cosine generator, as it uses the absolute position to generate the sine cosine, all the corrections of that are applied to the absolute position also apply to this sine cosine output here. So it's quite precise and accurate as well. All right, time to come close to a practical demonstration. So we have evaluation kits available for this device. There is a sensor board T-shaped sensor board, and at the edge here you can see the 5x7mm sensor package. The evaluation kit also comes with an LED module. It's a blue LED iC-TL46, 460 nanometer peak wavelength. You just put it on top of the sensor board, and beneath the LED and the sensor board, there is the code disk rotating then. We have an adapter board where you can connect the sensor board here. So you have easy access to all the encoder signals on that adapter board. Of course, code disk also out of one hand here, so you can start evaluating a real encoder system. So the 26mm code disk made of glass will come with the evaluation kit. And as for all programmable iC-Haus devices, we do have an evaluation GUI software where you can access all the chip parameters, all the chip registers here, program and calibrate the system. Therefore, you'll need an USB to serial converter. We have that available to make it easy for your evaluation. Okay, enough words said. Let's get practical. iC-RT2624 live demonstration. I will be happy to set up a 26-bit absolute encoder here with the device in minutes. Okay, so right to my next, there is the setup. And I first like to explain a little setup here. So taking one step to the right. So first, you see the code disk, the 26mm code disk here mounted onto a shaft. Underneath the code disk here, you can barely see it, but it's there, is the 5x7mm sensor package. Here's the sensor board that I just showed. And let me show you, just checking if you can see it, we're in the camera. Yeah, here's the LED module, the TL46 blue LED module. And well, I simply connect it onto this sensor board carefully. All right. Things set, encoder stack assembled. Aside from these components, everything is mounted onto an iC-Haus test stand, which, by the way, if this is helpful to you to get started in the lab, please feel free to reach out. We can provide it. It contains a motor with an integrated reference encoder, and extremely helpful are those micro manipulators here. So I can really fine-tune the mechanical alignment in Z-axis via this micro manipulator, in radial axis via this manipulator, and in tangential axis via this manipulator. Then the sensor board is connected to the adapter board, as I have showed, and via the sub-D connector here. It is connected to our latest BIS to USB adapter, high performance BIS to USB adapter, the MB8U. Since I want to show you a little bit of an accuracy measurement, we go into a BIS chain with this reference encoder inside the motor. That's it for the setup. I do not need to move too often. I will just start rotating the disk. Maybe we can do a close-up to camera number 3 here. So you'll see the disk is running at like a few hundred RPM or something. All right, then I will be operating the software next. So taking a step to the left and opening or sharing my screen first. All right. You should see my screen, do you? Perfect. All right, so this is the GUI software that you can download for free from our website to evaluate the chip. The adapter is set here to be used, set here at the top. And now, once I press connect here, the sensor is powered, and you will see the blue LED illuminating. Perfect, we are at the right camera, so I press connect here. Okay, LED illuminates, blue light, 460 nanometer, and now I can program the chip. To be fair, I'd like to have the same default configuration that you have when you would be delivered this device. So I just go to File, load a default configuration file, up into RAM. Okay, so the default configuration file has just been loaded. To be clear, everything is erased. What I did before, I write this default configuration to the EEPROM and I reboot the device. This is somewhat equivalent to a power cycle. Okay, so this is default factory parameter settings. On this first tab, all you need to do is tell the system which code disk it is reading. Since this is the standard code disk, this is already applied by default. I can just leave that by default. Things set. No further actions here to take. Next is I go to a system calibration. And there I go to the analog calibration at very first. I want to do an initial calibration in the current alignment state that the system is in. So I press adjust here, and when I do this, this is not like a software calibration, it's an on-chip calibration. So the software just triggers a command and the chip does a self-calibration. Okay, so I'll do that. Takes a little time, and then, well, if you're working with encoders, you're pretty much familiar with offset errors, all gone, gain amplitude errors between sine and cosine, all gone, and also some phase adjustment, a little bit of phase adjustment has been done here. So that's it for the analog calibration that is mainly responsible then for achieving best possible measurement performance, right? In terms of availability and robustness, the digital adjustment is what I need to do next. The digital adjustment makes sure that the system works within the huge assembly tolerances that I just showed. So on purpose, I did not do an ideal alignment here. I can show you that in a second. It's not ideally aligned what you see here, because I want to show you it just works if you're not ideally aligned. Same story, everything by default. It just press adjust. It does a self-calibration, and then yeah, we are basically finished with the main steps at least. So I do that. And you have two parameters here. There is a phase error that is corrected. So this is if you do have some tangential displacement, it would be related to this phase error here. And then there is a scale error. This is related to a radial displacement of the sensor versus the code disk. How you can make use of this, I'll show you in a second. But those steps, everything you need to do to get the 26-bit absolute position data now. I write the calibration values to the EEPROM. We do a reboot, so we start from scratch. We go into normal operation, and then we will read the position data. So writing to the EEPROM, rebooting again. So let's see, I press read sensor. There should be no errors or warnings lighting up, and you should see singleton data moving. Well, yeah, success, everything up and running. Here are the 26 bits of angle data. I can switch that to binary, so you see quite some bits of position data that you have available here now. Okay, so now some further tricks that you could do. If you want to get started in the lab, it might make sense to have as a starting point a somewhat golden device. So you want to have an ideal alignment of chip versus the code disk, so you can explore all the functionalities from somewhat best possible state. To reach that, you can make use of the digital adjustment that I'm in here. There's a possibility to dynamically set this adjustment so that the chip compensates for this phase and scale error in operation. And as I said earlier, it is related to tangential and radial displacement at most. So you can, if you do have access to some micromanipulators, you can just displace the sensor to its nominal position. So I'm setting the dynamic here for the phase 2, 3. This is a good starting point. By the way, there's an application note guiding you through all this, yeah? No need to write comments here. And scale the same. So the dynamic is now activated. I need to check the checkbox, read continuously here, and then I read the dynamic parameters. And you will see in those green, gray backed boxes here that there's a little bit of a flickering going on because systems are moving systems are not 100% stable, right? So you see the LSB here is flickering at the scale error, and same for the phase error. For the phase, the ideal position would be at 1 degree electrical here. So we're more than close enough to ideal position, but I'd like to show you is with the scale error related to the radial displacement. Therefore, I go to the side here, again using the micromanipulator for the radial displacement. So when I turn this knob, please look at the GUI screen here and see how the dynamic parameter changes. The target value that we want to reach is 1. 1.0 would be ideal. Yeah? Okay, let's do it. Okay. Wrong direction. Okay, now we're getting close. All right. All right, close enough. Yeah. So this is almost 1. Okay. Now I'm perfect, right? Okay. So I just tuned the mechanical alignment to a somewhat golden device state. Now I can leave that state again, disabling the dynamics, doing an adjustment again because I changed the alignment, right? Okay, so we have a golden device state. Write this to the EEPROM, things done and set. Reboot again because we displaced the system and we are back on track. Now let's have a look at accuracy and also what you can achieve with the eccentricity correction. So I press the adjustment eccentricity tab here. And before I press adjust or do the correction, I'd like to show you, even for this, let's say, by eye, very stable setup here, the impact, the critical impact of code disk eccentricity. So I press reference measurement here, and let me just activate it. All right. I've done it at training, so you see it already, but let's do it live. I just measure against the reference, and what you see here on the left, at the y-axis is the angle error, currently in degree, and here on the x-axis is the angle over 360 degrees. So I'm measuring, and you can see it's updated, so there is a significant long wave error in this system. By eye, you would never expect, by the way. And this has the impact of an absolute accuracy of plus minus 0.06 degrees. That's not what we want to reach, right? And now I can adjust the eccentricity either against the speed reference or against the reference encoder. I have a reference encoder here, which I love to make use of. So when I press this button, the eccentricity correction is applied, and you will see that everything here looks a bit smoother. Okay, that looks a bit more flat. I kind of need to adjust the scaling so we see where we ended up. Let's go to the 0.01 range. Okay, so we're within 0.004 degree, or even better, of absolute accuracy. I can change the scaling here to arc seconds. Okay, let's go like minus 20 to 20 arc seconds. Okay. Well, we're in the range of plus minus 8 arc seconds. Yeah, good catch. So single-digit arc seconds of absolute accuracy for this device now. Okay, so you've seen live performance, and there's one last feature that I like to show to you, which is a diagnosis feature I've not talked about yet. We have an on-chip contrast measurement, a digital contrast measurement that helps you identifying the quality of the optical projection. So it's right here at the bottom. And I'd like to enable it. Here, it uses one of the 4 analog signals for analysis, so the positive cosine in that case. And when I press read continuously here, you will get a live view of the signal contrast we currently have in the system. Let's do so. So we are roughly at almost 50% of signal contrast. And this is a pretty good indicator, one for LED and light quality, and second for air gap. And that's what I want to show as a last demonstration here. Then we have the summary. I'd like to change the air gap now here via the Z manipulator. And then you will see a change in the contrast value, right? So I must be careful. I don't want to scratch the code disk too much. All right. So going a little closer, and yeah, you see there is a change. The signal contrast is now a little better because I moved the sensor closer to the code disk. So that's it for the live demonstration. Hope you liked it. And well, I would be happy to exchange ideas and measurement results with you if you're interested in using this sensor in your lab as well. All right, so we should see the presentation again. I give a quick summary, and then Henrik and we're more than happy to answer the questions. All right, so 26 bits of angle resolution with this device is provided. We've seen typical angle accuracy below 0.01 degree, but as you've just seen, single-digit arc seconds are possible. We have those relaxed assembly tolerances really helping to relax your production processes, and also the mechanical tolerances in operation, so plus minus 0.5 millimeter in tangential and radial direction. Air gap also pretty high, up to 0.8 millimeter air gaps possible here. We have the robust contamination-tolerant sensing technology here integrated. You are free to, in the code disk diameter, thanks to FlexCode. So if there's a certain requirement in your application, just let us know, we can help you. And well, this kind of summarizes with the platform approach. This is meant to be a somewhat one-fits-all sensor solution for complete product lines, because you can just scale the code disk and you can just program the desired resolution on any encoder interface that's seen here. If you want to get in touch, please, you're more than invited to reach out to me. From my side, thank you so much for attending and listening, and yeah, happy to answer your questions.
Thank you very much, Sylvan. Your presentation was very interesting, and we've got a lot of questions, so let's move straight into the Q&A. And you can always ask questions during the Q&A as well. They will be forwarded to us. And should not all questions be answered, we will make sure that they will be responded to by email if we can't go through all the questions. So let's start. Sylvan, what's the max eccentricity for the system that you can allow?
Yeah, that kind of depends on, of course, on which code disk size you use. For the 26 millimeter code disk, I'd say it's in the range of 60 to 80 micrometer.
Okay. Next question. What is the tilt tolerance?
The tilt tolerance in terms of XY plane, this was the plus minus 2
degree.
2 degree, exactly.
Yeah. Okay. Good. Then I have another question about assembly tolerances. How do the assembly tolerances add up to each other? Which tangential and which radial tolerances are possible? And if the code disk has a distance of 0.8, what is then the gap, so to say?
Yeah, so that's a sharp, very good question. Actually, you can make use of the full tolerance range in XY plane.
Okay.
So this is more of a rectangle than like other shape of working area here. In terms of air gap, the illumination plays a big role. So the quality of the illumination is important to reach the 0.8 millimeter here. Definitely recommend blue light to go there and collimated light. So the system is capable of running within these tolerances, even stacked up. Yeah.
Excellent, good. Next question, can I monitor the contamination of the disk in production and later during operation? Is that possible?
Yes, you can, because the bit error correction that you set, by the way, it's programmable for the chip, how many bits you'd like to correct. And you get a live view of how many bits are currently corrected. So you can read that out, and that somewhat correlates to contamination. Yeah.
Excellent, good. Next question. I was always curious about the algorithm you use to generate the PRC scale. Could you share some details, maybe some documentation?
Well, we are happy to help you with the design. There's quite some know-how and also, let's say, some experience from our end involved in designing these code disks. We are happy to provide you with the files according to your needs. That's what we can do.
Excellent. Next question. If we pour the sensor in epoxy for IP protection, will the sensor be able to work properly?
Okay, the sensor in epoxy. Okay, well, you of course need to leave the window open. Otherwise, well, the projection will not reach the photosensitive area. If I got the question right.
Yeah.
So. Well, it would not be the recommended way of usage. That's something that we should discuss before doing so, I'd say. Yeah.
Okay, good. Is there a way to adjust eccentricity without a reference encoder?
Yes, against a speed. Yeah, you can apply a constant speed and then use the on-chip. It's also on-chip eccentricity correction that then computes the eccentricity.
Okay.
And compensates it for sure.
Good. The next question is, what's the production schedule? When can we plan on?
Yeah, that's an important one, and I'm happy to transparently answer this. So we're currently in a functional sample state. As you've seen, things work out very well here. Ecosystem is in a solid state. We will have, so samples are available and evaluation kits. You can get started with the system. Pre-series is expected end of Q4 this year, and then, well, next year we will go into series production. That's for sure too.
Excellent. Okay. What is the resolution of the reference encoder used during the accuracy measurements?
Yeah, I think it's a 27-bit reference encoder, but more important here is that it's accurate actually, yeah, than the resolution.
Okay, next question. No one-touch calibration is possible, like the TV, to achieve 0.01 degree using constant speed?
So one-touch calibration, yeah. It is a complete system on chip here, and in the short time I cannot go through all the features. So that's a very pleasant question here. Yeah, we have push-button calibration. You can use one of the GPIOs to calibrate the system, as I did with the software. You can do that by push-button or sending a digital command. It works out pretty well, yeah.
Okay. The next question is about code disks. So what are the code disks available other than 26 millimeters? I think you touched a little bit on it earlier. And what will be the max accuracy on that one?
Okay, yeah. So in general, the bigger the code disk, the more resolution you get out of it. Space resolution for sure. That helps with accuracy as well. Still, mechanics and eccentricity is something to get rid of. We have available as samples the 26 millimeter, 33 millimeter outer diameter, and a 39 millimeter outer diameter code disk, all as glass code disks. Yeah. So bottom line, the bigger you get, the more resolution you get, the more accuracy you can get out of the system. Yeah.
Okay. Next question. For customers already familiar with the iC-PZ family, how does the AIO criteria numbers compare to the RT?
Yeah, so they are a lot more relaxed. Of course, it depends on what you would like to achieve. In terms of availability, feel free to test it as our developers did in the photo that I just showed. I was impressed myself. The system really provided a reasonable absolute position, even with this absurd level of contamination. But of course, if you want to reach arc seconds of accuracy, well, that's a little bit of a trade-off that you have to keep in mind. Yeah, it's application specific.
Okay, thank you. So on to the next question. What's the max RPM the sensor can read? And what is the capacity of the sensor frequency?
Okay, yeah, so we have with the 26 millimeter code disk, we can reach up to 30,000 RPM maximum. The bigger the code disk, so it's a linear function, right? The bigger the code disk, then the RPM will be reduced a little according to the input resolution. But with the 26 millimeter, 30K RPM is possible.
Excellent, thank you. So next questions, can you provide the MCU drive for this iC-RT2624?
Of course we can, yeah.
Okay.
Simple.
Good, excellent. Next question, what is with multi-turn? Is it stored? What happens if you run into more than 360 degrees in the system?
Yeah, I did not touch multi-turn in this session here, probably in a separate one. Yeah.
Okay.
So there is a multi-turn interface where you can connect iC-Haus multi-turn sensors. For example, if you want to do gearbox multi-turn, we have iC-MV as gearbox scanners, magnetic gearbox scanners. Battery backed, we have the iC-PVL as a magnetic, straightforward battery backed up multi-turn. And we can also talk about some energy harvesting, for example. So yeah, there are possibilities, but not with, so it's a single turn device only, you need an additional component. Yeah.
Excellent. The next question, can you filter out the contamination during power up?
Filter out. So the bit error correction is working once the device is powered up, and then you get a feedback of how many bits are corrected. Yeah, you should have an indication there. But yeah, that's something we can discuss in detail, but I guess so, yeah.
Excellent, okay. For clarification, across multiple reboots, accuracy repeatability is less than 0.01 degree. Within one reboot, is there repeatability within 0.01 degrees? That's the question.
So the repeatability of this device, since really the noise-free resolution here is excellent from what we can provide to the system repeatability. The encoder electronics here are of excellent quality. Yeah, below 3 arc seconds, so 0.001 degree or a lot lower than that would be possible in terms of repeatability in the system.
Excellent. Okay, how is eccentricity adjust without using the GUI? Is it how do you do that?
Yeah, you can do that also by push button calibration. So there is just a few words about it. We have an integrated command stack where you can just throw in all the calibrations that you want to do by push button. And you can also use the eccentricity correction, then store everything in the EEPROM. You do not necessarily need any software to reach a high accuracy with this device and to set it into operation.
Excellent, okay. Next questions. What about the current consumption of the chip, for example, at 3.3 volts?
Yeah, that's something that I would need to look up. Yeah, we are probably in the 30 milliamps range, but depends on LED because the LED is also regulated by the chip.
Yeah.
So that's something that has a bit more of, let's say, boundaries to it to give a precise number. Yeah.
Excellent. Next questions. What are the maximum and minimum diameters for the code disk?
Yeah, so 20 millimeter is like the minimum, because then the curvature is getting too extreme for the sensor geometry. That's clear. If you go very tiny, then you have extreme curvature. So 20 millimeter up to, I'd say 80 is something that I can, yeah, I would be very enthusiastic about, but we are checking if linear would be possible as well. That's something we need to evaluate ourselves. But 20 to 80 millimeter, I think this is the range, and everything in between. Yeah, that's a highly customizable. Yeah.
Very good. We have a couple of more questions.
Yeah,
so
I'm
it's
ready.
A very
No
good
worries.
interactive session. So, another question regarding multi-turn. It has internal multi-turn available, or does it need to be an external one?
We need an external sensor, as I just said. We have an easy-to-use multi-turn interface, so you can just plug and play. Use one of our multi-turn sensors, you connect them, and it reads in the multi-turn and synchronizes it automatically to the single-turn position. So that's straightforward, but with an additional component.
Okay, good. The next one is about safety. Here's topics. Can you elaborate on the safety readiness?
Yeah.
Which position data is available in parallel?
Yeah, and so all the interfaces that you have just seen here are available simultaneously. So they are on dedicated pins. You have BIS, you have SPI, you have the two sine cosine interfaces, ABZ, even UVW, all on dedicated pins. You can use them. When it comes to safety, only the sine cosine signal path is the one that has a safety readiness to it, because the architecture within the chip design was focusing on it at an early stage. Yeah, this was a requirement, that we wanted to fulfill.
Okay. Next question is about LEDs. Do you have one to recommend?
Yes, I do have one to recommend, and it's from iC-Haus. Our iC-TL46 460 nanometer with the 3.4 millimeter spot size. This is the one that I've been using here. This is kind of fits to almost any applications. If you want to use 3.3 volts designs, the blue light requires a higher forward voltage, and this does not match. Then no worries, use infrared. We have the iC-TL85, 850 nanometer, lower forward voltage. You can use it in a 3.3 volts design.
Okay, I think you answered the next question, which is basically, do we need a more than 5 volt supply if we're using the blue LEDs?
Okay, so I anticipated.
You anticipated that one. So I think that concludes our Q&A session, and I really want to say thank you to the listeners here for the very good questions, very many questions. And if you have further questions, feel free to reach out to iC-Haus and Silvan in particular. We will support you and guide you through your experience in testing this device. So, without further ado, thank you very much to the podium, and an extra thank you to you, Silvan, for a good presentation. And we look forward to hear from you very soon. And thank you very much. And from the podium, bye-bye.
Thank you. Take care. Bye-bye.
iC-Haus. Integrated circuits.